All right, guys, let me know when you see me and give a shout out in the chat if you're there, just so I know somebody's there, somebody's hanging out. Um, once I see you, we will be working on square roots this evening. Square roots is what we are taking a look at. And as always, Ali is first there. Oh, Ibrahim's there too. Okay, so we got some people. All right. So I know we see me. I know it's time for us to get started. We are looking at square roots. So here's the deal. The whole basis of this really is this first problem here. If we can't handle this, then we can't handle really any of the rest, okay? And it involves putting this in simplest radical form. I'm going to show the two different options you have for doing that on this first one here, okay? I'll do that. But then after that, I'm pretty much going to stick to perfect squares method. Okay, so you have two choices here. You have perfect squares method. Okay, now these are not like super official names or anything like that. This is just kind of what I've chosen to call these things. Okay, and perfect squares method basically means you try to write it as something you can take the square root of. So a perfect square times any other number. Okay, and ideally, in an ideal world, you want to use the biggest number as humanly possible. So there's actually a couple perfect squares, 9 and 81, that both go into 810, but we'll choose 81 because it's the bigger number. So we're going to rewrite 810 as 81 times 10. Oops, sorry about that. And then basically what we're doing is we're taking the square root of the 81, turning that into a 9. We're trying to take the square root of 10 and realizing, oh, that's not a whole number, so we're just going to leave it as 10. And that's the whole deal. Okay, if you were doing factor tree method, you basically, well, make a factor tree for the number. Okay, so we'll go 81 and 10. We'll go 9 and 9 for the 81. 3, 3, 3, 3, and 5 and 2. Okay, and after you make that factor tree, though, the way you're trying to rewrite it is with as many 2 exponents, so as many square exponents as possible. Okay, so instead of writing the typical 3 to the 4th times 5 times 2, we will instead choose to write it under the square root as 3 squared times another 3 squared times 5 times 2. The reason we're going to do this is because when you take the square root of something with a squared, the squared and the square root cancel out, and that's really the whole thing. Okay, so square root of 3 squared is 3. Square root of the other 3 squared is also 3. 5 and 2, we can't take the square root of either of those without getting a decimal. Then I combine everything, and I make it 9 root 10. So I get the same answer no matter what. One involves a little bit more work, but one involves you kind of having to think through some numbers and do a little mental math. Okay, so there's pluses and minuses both ways. Guys, I will be sticking to perfect squares method the rest of the way. So basically, if at any point you see that you got something wrong or something different than what I got and you're not sure why, if you were using factor tree method, I would double check that. That might be a good place to check initially. Okay, multiplying. Rules for multiplying are really pretty simple. If you multiply, you are allowed to multiply stuff that's outside by other stuff that's outside and inside by other stuff that's inside. Beyond that, you don't really have a whole lot of choice, okay? Now, the thing is, what you can do is you can choose to simplify first or you can choose to not simplify first. There's no necessarily right or wrong answer. But for this particular problem, since I don't really feel like doing 18 times 30, I'm going to simplify it. So I'm going to change the 18 to 9 times 2 and rewrite that as 3 root 2. So now I've got 3 root 2 times 3 root 30. Now I'll multiply them together. I'll get 9 from my 3 times 3, and I'll get 60 from my 2 times my 30. Okay? And now when I multiply those together, or I'm sorry, when I try to simplify that, 4 is the perfect square that goes into 60. It's 4 times 15. Okay. Here's where I will make sure I actually kind of show my work here. That 4 I'm going to turn into a 2. Okay. But I've still got my 9 on the outside. I'll combine those and make it 18 root 15. Okay, guys, there were a couple different paths to a right answer there. You could have simply multiplied 18 and 30 right off the bat and gotten 540. So you could have done that. You could have said, okay, 3 root 540, and then gone from there. Guys, I'm really not a huge fan of, I like to simplify right away. Because to me, figuring out the largest perfect square that goes into 540 is a little bit tricky. It turns out it's 36. Okay, so this would become 36 times 15. I think for most people, though, that's tough, especially if on the mental math aspect of things. I could do the way I did this over on the left side all in my head. Okay, I get to the same answer no matter which way I tackle it. And there's other potential shortcuts you could take too, but really, honestly, guys, that's probably what I would be doing. I would probably simplify first, unless I felt like I could do the mental math in my head. Then I probably wouldn't. Okay, for addition and subtraction, the rules are pretty much the same as variables. If I've got the same variable, I add the coefficients, the numbers that are right outside those variables. Same thing with the root. So right now, there is nothing I can add and subtract. Nothing. Nothing, 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 nothing. Okay, I cannot add or subtract any of those numbers because they don't have the same thing under the root. So what I'm going to have to do is attempt to simplify every single one of those. Okay, so I get 25 times 7. We'll work on that one. 4 times 2 will work for my 8. And 64 times 2 will work for my other one, okay, for my 128, okay. Now, I'm going to simplify each of those, okay, so I still have my negative 3, square root of 25 turns to 5. Same thing on this one, I keep my 3, now I try to take the square root of 4, square root of 4 is 2, oops, nope, no square root, shame on me. And the 2 stays. Same thing in the last one. I've still got my 3 that was on the outside. The square root of 64 is 8. Square root of 2 stays. Guys, I'm trying to do a good job of lining things up in case you're forgetting where things come from. Okay, so look, there's all my outside numbers. Those are all still there. Okay, there's all my perfect squares. Okay, all I did is actually take the square root. And then there's the stuff that I wasn't able to take the square root of. Okay, now at this point I'm just simply following order of operations. So I get negative 15 root 7 plus 6 root 2 plus 24 root 2. Now if I look, I have 2 like terms. It's those last 2. Okay, those are my like terms. I can add those and get 30 root 2. And my negative 15 root 7, I just can't combine with anything. And I'm all set there. Okay. Those are your basic operations. Now, guys, when we get into division, which is what we're about to do here with this fraction problem, the one difference we add is you're not allowed to have square roots in denominators, okay? And there's lots of different ways that you can deal with that. I'm actually going to show you 2 different ways you could deal with this problem. And they're roughly equal, but there's pluses and minuses to kind of doing it both ways. I want you to see both ways. So, in and of themselves, there's nothing wrong with 15 or 10. There's really nothing at all there that's wrong, okay? So like you can totally just get rid of the 10 right away in the denominator, but you don't have to simplify any of these roots. So I'm going to do that way first. I'm just going to multiply by square root of 10, okay? When I do that in my denominator, I get 5 times 10. Basically, the idea is when you multiply 2 of the same square root, they cancel each other out because you're squaring it. Squaring and square rooting cancel each other out. On the top, though, no such luck. I just have to multiply the 15 and the 10 and get 150. Okay, now here's where the difference comes in. I now have a square root on top that I do need to simplify. Okay, so I'm going to use perfect squares method, make that 25 times 6. At the same time, I might as well do my math on the bottom, change that to a 50. Okay, That changes to 4 times 5 times the square root of 6 from taking the square root of 25. I get 20 root 6 over 50. And then last but not least, whoosh, cancel. Okay, simplify the 20 over 50 to 2/5, and I get 2 root 6 over 5. Okay, that's kind of your like traditional way of handling this. Okay, your less non-traditional way of handling this would be to try to simplify right away. Okay, so I'm going to rewrite the problem. And basically the whole idea is this: if two numbers are under a square root, you can simplify them. You can divide them. So I can simplify, I'm sorry, that's a really terrible 10. I'm going to fix it. It's going to bother me. That was only marginally better. You can simplify the 15 and the 10. That is okay because they're both under a square root. Same reason you can multiply them both. Okay, so I can change that to 3 and 2. So now I've got, sorry, I should use a different color. I'm using blue. 4 root 3 over 5 root 2. So that's just from that initial simplification. Now I can multiply by square root of 2 to get rid of that. I get 4 root 6 over, that turns to a 2, so I get 5 times 2. 4 root 6 over 10. Simplify the 4 over 10 and I get 2 root 6 over 5. I get the exact same answer. One's not necessarily better than the other. I typically will try to simplify them first if I can, but sometimes that's not always possible. So it's good to know that you can kind of handle this both ways. Okay, all that's left in 5 and 6 and a little bit 7 too is basically we're going to start applying skills. Okay, so now we're not really learning any new skills, we're just applying them to unique situations. Okay, so here we're applying the concept of multiplying polynomials to what we already know about our ability to multiply square roots. So basically you're going to do root 3 and distribute, and you're going to do root 2 and you're going to distribute. Okay, I'll keep my colors the same so we can at least kind of get what I'm doing here. So square root of 3 times negative 3 root 3 turns into negative 3 times 3. Right? Because when I multiply the square root of 3 times 3, it cancels out and I just get 3. Go over to the 2, I just get plus root 6. Root 3 times root 2 is just root 6. Okay, now I'm going to distribute my square root of 2. I get negative 3 root 6. Okay, all I'm doing is multiplying the square root of 2 and the square root of 3 together. Okay, and then last I multiply root 2 and root 2 and I get 2. Okay, I'm going to do some rewriting here really quickly. Negative 9 plus root 6 minus 3 root 6 plus 2. And now we just combine like terms. Those are like terms. They make negative 2 root 6. And those are like terms. They make negative 7. So that was just combining multiplying polynomials with square roots. The skills really aren't any different. It's just doing multiplication 4 times, and then you have an addition or subtraction problem, both of which we kind of already did. Here's the one. Okay. This was a struggle for pretty much everybody. Okay, initially. This is a very challenging problem, and the reason is our instinct tells you to just multiply by the square root of 3. Okay, you can't do that. It's not going to work. Okay, because what will have to happen is you'd have to distribute here. So it would end up getting rid of the square root of 3 there, but it would end up putting it over with that 4, so that's not going to work. What you have to do is you're using the same relationship as you use when you use difference of squares rule. It's called the conjugate. You're basically going to switch that symbol in the middle, and you're going to multiply by exactly that. Okay, so instead of 4 plus root 3, you're going to say, I want to get rid of 4 plus root 3, so I'm going to multiply by 4 minus root 3. Here's the reason this works. In the numerator, we distribute 16 minus 4 root 3. So I'm totally just distributing the 4 there. On the bottom, I'm going to show you the whole multiply out process. So like we're going to do 4 times both of these, and then we're going to do root 3 times both of these. We're going to distribute twice. Okay, so when I distribute the 4, I get 16 minus 4 root 3. when I distribute the square root of 3, which I'll do in blue now, I get plus 4 root 3 minus 3. Square root of 3 times square root of 3 is 3. You notice what happened with those two? Those cancel each other out. They add to 0. Okay, and that is going to happen every single time when you multiply by the conjugate, because you're always going to be doing that same multiplication with both a plus and a minus. Okay, so those will go away, and this is why it works so effectively for canceling out your roots. Okay, so plopping things in, we get 16 minus 4 root 3 over 16 minus 3 is 13. No need to simplify here because 13 is a prime number. Okay, so again, you're always multiplying by the conjugate. It's that whatever you want to get rid of with the opposite sign in the middle. Okay, simplifying when you have variables involved is really not so bad. Okay, the 48 will work exactly the same way. Okay, basically what I'm going to do is this. I'm going to break up 48 into 16 and 3 because that's a perfect square. And then all I would do for the variables is break them up into as many perfect squares as possible. Well, this one's kind of already done for me. This is maybe not the greatest example. I should have looked a little more closely at this. We'll try another one. But basically, I've broken this up into as many perfect squares as I possibly can already. There's a perfect square because I can take the square root of it, and there's a perfect square because it has a square on it. Okay, the square root of 16 is 4. The square root of x squared is x, and what I have left is 3y. Here's kind of the main reason for doing this problem, though. I need to put absolute values around my x. Okay, and the reason is, if you had started with a negative for x, it would have ended up positive, okay? But when you have that single x out there, that could possibly be negative, so you have to force it to be positive by putting absolute values around it, okay? Really, the shortcut, especially for square roots, is this. For square roots, if you moved any variables from the inside to the outside, they need absolute values if they could be negative, okay? So let's take I'll actually give you kind of a quick, hopefully more mental mathy example for this. We won't use any numbers, we'll just use variables. Let's go square root of x to the 5th, y to the 8th. Okay, if you want to take a quick second and think about that, try to work that out, feel free. Basically, the longhand way of doing this would be to write as many x squareds as possible. X squared, and x. That's my 5 x's. Okay, and then for the y's, 2, 4, 6, 8. Okay, because basically what you know is anytime you write a squared, it's a perfect square. Okay, anywhere where you see those squares, those are all the ones that get to come outside of the root. Anything that doesn't have a square, like that little lonely x, has to stay inside the square root. Okay, multiply things together, and we get x squared, y to the 4th, square root of x. Take a second to think, do we need any absolute values here? Basically, the question you should be asking yourself is, can anything that's outside of the root now be negative? I'm hoping you're mentally thinking to yourself, no, we don't. X squared is always going to be positive because we'll have an even number of negative signs. Same thing with y to the 4th. Okay. Reminder, the way to shortcut this problem, instead of writing out all of those squares, is to just divide those exponents by 2. Basically see how many times does 2 go into it. 2 goes into 5 2 times with 1 left over. That's why I had 2 x's on the outside and 1 on the inside. 2 goes into 8 4 times, and it goes in evenly. Last one is solving for x, or in this case, apparently a k, because why not? Okay, when you are, Ali asked a good question that I'll actually stop on and do right away here. He said, if you put absolute value when it isn't needed, would it be considered wrong? This is more, for square roots, I would say no. Like if you put absolute values around this, the thing is they're redundant. Okay, if we get what that means. Like basically they're completely unnecessary, but they also don't change anything. Okay, because you're forcing something to be positive that's already positive. Okay, if you put absolute values somewhere where not only are they not needed, but they change the value, then I would argue that that is wrong, okay? But that's probably more of a discussion when we're working with roots that are not square roots, okay? So for square roots, you're probably safe. For other roots, if you want an example, come talk to me at some point and I can show you an example of when putting absolute values would be wrong. But for square roots, especially if variables are involved, you should be safe. Okay. When you're solving for square roots, biggest mistake people make. Biggest mistake people make is they forget to isolate the square root first, and they try to just square everything right away. Okay, you cannot do that. Okay, because that would be distributing an exponent over addition. You have to isolate the square roots first. So I'm going to subtract 5. I get 8 equals square root of 11k minus 2. Now I should square both sides. Square, square. I get 64 equals 11k minus 2. So over on the right, squaring the square root simply canceled it out. That's all it really did. Okay, it just got the square root to go away. Okay, now at this point, I'm really just solving for k or for x or for whatever variable I have. Add 2, 66 equals 11k. Divide by 11, I get k equals 6. Now here's the big deal on these problems. You do need to actually plug them in and check. Okay, this is when you get one answer. Could it be wrong? Yeah, it's not often, but yeah, no, it totally could be. If you get 2 answers, especially like if quadratic formula was involved or something like that, yeah, then you definitely want to go back and double check because you could have what's called an extraneous solution. Okay, you could have a solution that even though you thought you did all the math right, it didn't work when we plugged it back in. If we plug this one back in to the original, I'm going to show the work. Okay, basically it looks like this. But if we do order of operations here, we end up getting 13 equals square root of 64 plus 5. 8 plus 5 equals 13. Last I checked, that's true all day, every day. So we are fine. K does equal 6. But with square roots and fraction-based equations, which is really what our last 2 of these reviews were about, when you get to the equation part, you do need to make sure and check that your answers are actually right. CC asked a good question, and it's related to if you're in regular algebra, you might not get this now, but we'll be talking about this week. You only put absolute values on even roots, squared and fourth roots with odd exponents. Yes, so even roots are the only ones where you need absolute values, and it would have to be something that could potentially be negative on the outside. So yeah, that would be a negative root. Okay, that is it. That's all we got. Nothing left. Little quick on square roots there. If you have additional questions, or especially if you're watching this afterwards and you weren't able to ask me anything, if you have questions that came up as you watch this, come talk to me and let me know. We've still got a little time before exam next week, Friday. Hope this helped. Have a good night.